Hello, this presentation is entitled Electrophilic Aromatic Substitution, 5 Main Reactions. In this talk I will be discussing the general reaction called electrophilic aromatic substitution, comparing it with nucleophilic substitution, which you're already familiar with, and then talking about the 5 main reactions that fall into the category of electrophilic aromatic substitution. Okay, first of all, what is substitution? Well, obviously we're replacing one atom on a molecule with a different atom or a group of atoms. In nucleophilic substitution, we start with an alkyl halide, that is a concentrated or a saturated carbon, sp3 hybridized, and a halogen, remember that's chlorine, bromine, or iodine, and then a nucleophile, which is a molecule which has a pair of electrons and may or may not, but very often does have a negative charge. And in that reaction then, the nucleophile becomes attached in place of the halogen. So what's being replaced is a halogen atom, or a good leaving group, something that can leave with its pair of electrons. Notice this pair of electrons leaves with the halogen, and it therefore becomes negative. That's nucleophilic substitution, in which a nucleophile with a pair of electrons replaces a halogen. In electrophilic substitution, we're going to, on an sp2 hybridized carbon and a hydrogen attached, we're going to be reacting it with a compound called an electrophile, which is the opposite. Instead of having a negative charge with a pair of electrons, it's something that's electron deficient. It's lacking a pair of electrons, so it has typically a positive charge or something very close to a positive charge. And instead of replacing a halogen, we're going to be replacing a hydrogen. So the net result is going to be that the electrophile replaces an H+. So everything is the opposite. In electrophilic substitution, it's an electrophile that comes in, something that's positive, and replaces a hydrogen. In nucleophilic substitution, it's something negative that comes in and it replaces a halogen. So keep those in mind as we go through the reactions here in a minute. Okay, as I said, there are 5 main electrophilic substitutions that happen on benzene rings. So I'm going to draw a benzene ring here, and I'm specifically going to draw one hydrogen atom on it. As you know, there may be 5 other hydrogen atoms here, or in some cases there may be other groups attached to the benzene ring. If there are other groups attached, it makes the reaction a little bit more complicated, and we'll consider that in a future video. But for the moment, let's just focus on a hydrogen on the benzene ring, and let's react it with various kinds of reagents that will give us an electrophile to substitute on in place of the hydrogen. One of them is called nitration. And in this reaction, we're going to react the benzene ring with nitric acid. Notice that's concentrated nitric acid. And we're also going to add concentrated sulfuric acid. Notice that that's very severe conditions. Concentrated nitric acid dissolved in concentrated sulfuric acid. Not something you want to stick your finger into, obviously. The net result is going to be that we will attach a nitro group onto the benzene ring in place of hydrogen. So hydrogen will be replaced. We will write the balanced equation for this reaction when we consider the mechanism of the reaction, which we'll do in a future video. But for now, we'll just outline what is the reagent. Essentially, we'll write it as nitric acid and sulfuric acid. Then you replace the hydrogen with a nitro group. Now, very important question, can this reaction continue? Because, of course, there may be other hydrogens on the benzene ring. And the answer is, it's slower to do it again, but it is possible. So if we add more concentrated nitric acid and concentrated sulfuric acid, I'm just going to write it as nitric and sulfuric. Perhaps we wait longer, perhaps we heat it, but somehow we increase the conditions. It is possible to put a second nitric group on. It's going to turn out that if you do that, and by the way, you can stop it so that it's possible to synthesize nitrobenzene very easily from benzene itself by just doing this once. You can stop the reaction. If you add a second equivalent and you do it under more severe conditions, you can add another nitro group. And it turns out it's always going to go in the beta position, and we will learn why, again, in a future video. I know I keep putting you off, but that's the way it is in this chapter. Is it possible to add a third nitro group? Yes, but it's extremely difficult and probably not something you would want to do because it turns out that trinitrobenzene is very explosive, as is trinitrotoluene. Trinitrotoluene, what's that? TNT, very explosive. It turns out trinitrobenzene, if you were to put a third nitro group on, is even more explosive than trinitrotoluene or TNT. So generally you don't do that, but it is possible. In each case you have to make the conditions more severe to put a second and then a third nitro group on. Okay, so that's the first of our 5 reactions, nitration. The second of the 3 that we're going to consider, of the 5 we're going to consider, is called halogenation. In this reaction, again, we're going to start with a benzene ring having at least 1 hydrogen, and again, there may be more hydrogens, there may be other groups on here, but 1 hydrogen at least. If you react it with just the element, Br2, or Cl2, and again, we're going to use X as a symbol, it stands for Cl or Br, and a catalyst, a pretty strong Lewis acid catalyst called iron tribromide, or iron 3 bromide to be technically correct, which is a strong catalyst, then a reaction occurs, and in fact you can replace the hydrogen with a halogen. Okay, and so that's a reaction we'll discuss a lot more in the future, but the same question arises. Because there may be other hydrogens on the benzene ring, is it possible to do this reaction a second time? And the answer is, again, yes it is. But you have to use more severe conditions. And so if we add a second equivalent, it should be FeX3, if we're going to be consistent here. And let's use FeX3 here. In other words, if you use chlorine, the element chlorine, then you should use iron trichloride. If you use the element bromine, then you should use iron tribromide. Same thing here. In other words, the halogen should match, and that way you don't have any problem with mixing up the halogens and getting perhaps a different one attached instead of the one you want. So let's make this an X as well. Okay. Anyway, the fact is, when you add a second equivalent, which is possible, but you have to make the condition more severe, it turns out, interestingly enough, that you do in fact put a second halogen on, but in the para position. That's very strange, because with nitration it goes on in the meta position. Again, we'll learn why in the future, but just for the moment, keep that in mind. Question arises, could you add a third halogen? And the answer is yes. If there are positions available, which there would be typically, you could add a third one, but again, you have to specifically try to add a third one. It's not going to happen automatically. Okay. So that's the second of our reactions, called halogenation. The third reaction is going to be called sulfonation. And in this reaction, we start with a benzene ring having a hydrogen, and probably more than 1 hydrogen, but at least 1. And we're going to add a reagent called fuming sulfuric acid. Now, what fuming sulfuric acid means is that it's super concentrated and it has the gas SO3 dissolved in it. So they take concentrated sulfuric acid and they bubble sulfur trioxide into it. So it's really sulfuric acid with SO3 in it. Essentially the SO3 absorbs any water that might be in the sulfuric acid and then continues to add more SO3 into the water. So it's an extremely powerful reagent. As you can tell from the ones we've talked about so far, all of these reactions require some very powerful reagents to happen. They don't happen very easily. But the net result of this is that we add a sulfonic acid group. So we end up with benzene sulfonic acid on the benzene ring in place of the hydrogen. You might question, does that hydrogen end up being that hydrogen? And the answer is possibly. When we look at the mechanism later on, we'll consider that possibility. And another question arises, could you put a second sulfonic acid group on if you wanted to? And the answer is it's very difficult. Normally it doesn't happen, but it is possible. So let's go ahead and say, sure, let's do a second one. And if you do, where is it going to go? Turns out it's going to go meta So just to review, if you put a first nitro group on and then a second nitro, it's going to go meta to the first nitro. If you put a halogen, bromine or chlorine on, and then you put a second one on, it's going to go para to the original halogen. If you put a sulfonic acid group on and then a second sulfonic acid, it's going to go meta to the original sulfonic acid. All that will be made clear in the future. Okay, our fourth reaction has a person's name, actually two people's name associated with it. It's called Friedel-Crafts alkylation. So alkylation is the actual thing we're doing, and as the name implies, we're going to be replacing a hydrogen on the benzene ring with an alkyl group. So hydrogen, we're going to react the benzene ring with a hydrogen with an alkyl halide. So this is the first one of the 5 reactions where it's actually another organic molecule that you're reacting with, and not just an inorganic stuff. This is maybe ethyl chloride, it may be isopropyl bromide, it may be any of various alkyl halides. And then we're going to put in a very powerful, again there's that word, very powerful, Lewis acid catalyst, aluminum trichloride. Okay. And the net result of this is that you attach an R group, onto the benzene ring. Now, one thing that we should point out here is that the R group may be rearranged. Meaning that, let's say this were a secondary alkyl halide and it could rearrange to a tertiary, you're going to rearrange to a tertiary. That suggests that the mechanism for this reaction must involve carbocations, because if you remember, carbocations undergo rearrangement, whereas other intermediates do not. And since this undergoes rearrangement, it's probably a carbocation mechanism, and if you guessed that, you would be correct. When we get to the mechanisms in a future video, you will see that there are indeed carbocations involved. Another question that arises is, can a second group go on? Now this one is different, because the fact is, not only can a second group go on, but a second group always goes on, and that's because it turns out that a carbon group on a benzene ring activates it, makes it more active to future electrophilic substitution than it otherwise would be. And so, even without trying, you will in fact put on a second one. And it turns out it's going to go in the para position. Like the halogens, it directs a second group into the para position, unlike nitro groups and sulfonic acid groups, which direct to the meta position. So a second group goes on, and in fact, it's really impossible to stop it after one, even if you only put one equivalent of the alkyl halide in, because this ring is more active than this ring. It competes successfully for the excess reagent, and it continues on. This group then is even more active than this one, so this one will compete successfully with either one of these two for more of the reagent, and a third group will go on, and possibly a fourth group, and possibly a fifth group. So the fact is, Friedel-Crafts alkylation is not particularly good for synthesis. And that's because it gives a number of different possible products, and you can't really limit it to just one possible product. It gives mono-substitution products, di-substitution products, tri-substitution products, tetra-substitution products, and so on. Okay. Nevertheless, it's a reaction that we will be learning in this chapter, and we'll learn the mechanism of it, and we'll find out why an alkyl group makes the benzene ring more active to further substitution than the nitro, the sulfonic acid, and the halogen groups do. Okay, so that's Friedel-Crafts alkylation. Let's also put a star by it, because it does make a carbon-carbon bond. Notice that this is a new carbon-carbon bond that wasn't there to begin with, but again, it's hard to control, so it's not a particularly good reaction. We will learn other ways of putting alkyl groups onto benzene rings that are useful synthetically, but this is not one of them. Okay, then let's learn our fifth electrophilic substitution reaction. And this is also called Friedel-Crafts. So the people who developed the Friedel-Crafts alkylation also developed the Friedel-Crafts acylation, which is the reaction we're learning now. Similar type of reaction, a benzene ring with a hydrogen. We're going to add now, not an alkyl halide, but an acyl chloride. Remember what acyl chlorides are? We sometimes call them acid chlorides. They are the derivative of carboxylic acids. Remember acyl chlorides, amides, esters, and all those. Well, one of those is acyl chlorides, and it turns out they're useful in this particular reaction if you react them with a benzene ring having a hydrogen. And again, using the same catalyst, aluminum trichloride, you can put an acyl group onto the benzene ring. So we make a compound which is what kind of molecule? Carbon group on one side, carbon group on the other, C double bond O in between. That's a ketone. It's called an aroketone because it has a benzene ring on one side of the ketone. And this other side may also be a benzene ring if there's a benzene ring in this starting material as well. So you could have a diaryl halide, but not necessarily. But at least one benzene ring has to be there. Does the R group here undergo rearrangement? Nope. It's a very clean reaction in that there's never any rearrangement, so you can control what the R group is very easily. And then finally, the last question, does it undergo a second reaction? And the answer is no. No further reaction. So it always stops after just one, and you can't make it go any further. And we'll learn a little bit more about why that's true, but I'll give you a hint that basically both Friedel-Crafts reactions, Friedel-Crafts acylation and Friedel-Crafts alkylation, do not react with highly deactivated rings, and this is a highly deactivating group, which we will learn about in the next chapter, so they don't react. Okay. All right, we'll stop at that point, and we'll learn more about the mechanism in a future video. Thank you for your attention.